A tornado is the most violent severe weather phenomenon on the planet, and it's basically a rotating column of air that makes contact with the ground. That's the very simple definition of a tornado. And the tornadoes that we recognize are those well-defined laminar funnels that go all the way to the ground. And basically all the funnel is composed of, in addition to the debris that is contained within it, is water droplets. And so all a tornado is a rotating fog bank. When you're intercepting a tornado, and even when you get really close, it's very translucent. It's just really strong wind and it looks like fog. And when you're inside the tornado and there's not too much debris, you can actually see out. But it's when all that dust and debris kicks up that you can't see anything inside a tornado.
Windows up.
Drop down or not?
Drop your window down.
Right here.
It is crossing the interstate right now.
Drop down or no?
Down, leave it down, leave it down. Yes, it's a damaging tornado right on I-35.
Right here.
Right, you're fine, you're fine. We're going inside. Blast through, we're going inside. Look straight ahead. Jim, look straight ahead. We're in the tornado.
We're actually in the tornado right now.
You shoot straight ahead.
We're driving through the tornado.
Get in there.
We're driving the tornado with the Dominator.
Get in there, we're inside it.
We're in it, guys. We're in it right now.
Now drop down. Stop, stop, stop. We're inside. Drop it down. Drop it down. Drop down.
Drop down. Put it down. Put it down.
Are you guys seeing this?
We got it.
Holy.
Wow.
Before we discuss the forecasting of tornadoes, it's important to understand the underlying ingredients that need to be in place for their formation. One of the main ingredients for supercells and tornadoes is wind shear, and that's that changing wind speed and direction with height that we hear so much about. And imagine two pieces of paper, one at the low levels that's moving very slow, and one just above it that's moving very fast. And that creates a horizontally rotating tube. And there are all these horizontally rotating tubes that exist. They're invisible in the atmosphere before the storms form. And imagine an updraft moving over that. That'll flip that horizontal tube into the vertical. And very generally, that's how the rotating updraft of a supercell storm will form. And you also need other ingredients that are called the thermodynamics of severe weather. And that's the instability that we always hear so much of. And what drives instability is heat and moisture. And usually that tropical moisture feeds northward from the Gulf of Mexico ahead of approaching storm system. And then you have cold air above it, and that creates an unstable configuration. And we have that warm, humid air at low levels and the cold air at very high levels with an upper level storm system. That leads to CAPE, or convective available potential energy. And when those values get really high, it creates what's called a loaded gun. The heating of the day will intensify, and right near peak heating, when you get that moisture and that storm system ejects, you can have explosive thunderstorm development. And if the wind shear is sufficient, that changing wind speed and direction with height, then those storms will start to rotate and potentially produce tornadoes. But you do need the wind shear to be in place, and you also need sufficient instability, or that heat and moisture for a given setup to get tornadoes. If you remove any of those ingredients, or if they're just a little bit off, that can mean the difference between a long track violent tornado and no tornadoes at all. So in addition to the wind shear, that changing wind speed and direction with height that causes the storms to rotate, and also the heat and instability, which leads to the strong updrafts in the thunderstorms. You also need an upper level storm system and a surface front, and that can be a dry line. It could be a cold front, which separates cold air from warmer air to the east, and it could be a warm front. You get those east-west boundaries, usually on the north side of a heat and moisture return from the Gulf. You get the cold air to the north, the warm, humid air to the south, and you get a warm front. And usually you'll get increased wind shear along those warm fronts as well. And a dry line is something that's very unique here to Tornado Alley. It's perfect for supercell storms because of the orientation of the dry line, and it's not like a cold front where you have cold air undercutting the storms, and then that prevents them from reaching the heat and moisture at low levels. When you have a dry line, storms will line up along them and then move off that dry line, and dry lines are the perfect type of front to have supercell storms and outbreaks of tornadoes. But in addition to the wind shear and the heat and the moisture, or the instability, you also need that trigger mechanism, which is the upper level storm system and the surface fronts where the winds converge and they have nowhere to go but up, and that helps to encourage thunderstorm development. Because even if you have perfect instability and perfect wind shear for tornadoes, if you don't have a thunderstorm, you're not going to have any tornadoes at all. And so you need to have those fronts at the surface that will help organize those storms and initiate them, and then they'll take full advantage of that wind shear and the heat, moisture, and instability. And when all the ingredients are in place, it's incredible how efficient these supercells are at producing tornadoes. And a supercell storm is a storm with a rotating updraft. And a thunderstorm usually consists of an updraft where all the unstable buoyant air is lifting up, and you just see those explosive thunderheads that look like cauliflower plants, just real crisp, just like nuclear explosion like clouds. Those are the updrafts of a storm. And then you have the downdraft part of the storm, and that's where all the rain and the hail falls. And through evaporational cooling, as that rain and hail is falling, it cools even further, and that creates a downdraft. And so a supercell storm that produces long track tornadoes has the perfect balance between the updraft and the downdraft. Because if the wind shear isn't quite right for supercell storms, or the instability is a little bit limited, you'll a lot of times get the outflow outweighing that inflow, and it'll undercut the storm and prevent it from accessing that instability, rotating and producing tornadoes. But when they're in perfect balance, it's almost like the supercell is a living, breathing organism. So a supercell storm, by definition, is a storm with a rotating updraft, and that rotating updraft is called a mesocyclone. And if the wind shear and all the ingredients for tornadoes are in place, that mesocyclone can tighten into a tornado.
Most amazing pancake stack I've ever seen. It's that textbook mesocyclone. If you look up, this is a mesocyclone is a rotating updraft. That's a supercell thunderstorm. And this is the most textbook visual observation of a mesocyclone I've ever seen. This is a pancake stack. You can see why we call it that. All the way up. So it could easily produce a tornado too. Look at this thing. And we're sitting just east of it at 183 waiting for it.
So when I'm forecasting severe weather and forecasting a target area, we need to be within range of any possible tornado producer. Typically, I start off at higher levels in the atmosphere when I'm forecasting. I start off at about 300 to 500 millibars, and instead of using height coordinates, in meteorology we use pressure coordinates. With pressure, the higher above the ground, the less weight or less atmosphere exists above you, so the weight of the atmosphere above any given point higher up above the ground is less. And so that's why when you're moving up at higher levels in the atmosphere, the pressure goes down. And so at the surface, we're usually at about 1,000 millibars. That's the weight of the entire column of air above us. Whereas at 300 and 500 millibars, that's higher up in the atmosphere. And that's where that jet stream resides. That's about 15,000, 30,000 feet where planes fly. And that faster river of air called the jet stream, when that forms trough and ridge patterns, that's when the weather can get active. But it's underneath those ridges, which is a high pressure and anticyclone, that you get calm, tranquil, and clear conditions. But ahead or underneath the trough, upper level trough, that's where you get the stormy, rainy conditions that we seek as storm chasers and extreme meteorologists. And so when I look at when I'm forecasting, I first start off at 300 to 500 millibars, and typically the computer forecast models beyond about 7 to 10 days out are not very accurate. So if you're looking that far out, you're just trying to find something exciting to latch onto. However, within about 7 days, that's when they start picking up on those large-scale troughs, and it's the real big, deep troughs of low pressure that will create the severe weather outbreaks of a very large region. Because in those troughs eject from the Rocky Mountains, the southerlies ahead of them, or that low-level jet stream that we talk so much about, that pumps that heat and moisture northward from the Gulf of Mexico. And when the cold air aloft, with that trough of low pressure, basically it's a cold pocket of air aloft, when that moves over that warm, humid air, that sets the stage for a potential loaded gun environment, which is what we call an explosively unstable environment in storm chasing. And that could lead to the very strong supercell storms and those strong updrafts that can stretch those horizontal tubes caused by wind shear in the warm sector into the vertical. So now I'll take you through what it's like, starting with the morning of a tornado outbreak and going all the way through the storm chase. I'll wake up in the morning, slam an energy drink or two, probably not take a shower. I'm probably usually wearing the same clothes or underwear that I've worn for the last week or two, depending on if it's in the heart of the storm season or not. Immediately look at the computer forecast models and all the different models. There's several different ones. I'll look at all the variables, starting off higher up in the atmosphere at the jet stream level to analyze those troughs and find out how it's evolved over time, how consistent are the model runs, is there a huge discrepancy amongst the runs. You're usually aware that there's an upper level trough, so you want to start looking at the fine scale features, the surface observations. You try to find the position of the fronts. You'll look at radar the morning of to see if there's like a big blob of storms or rain that might act to limit the instability. Variables such as helicity, which is a measure of wind shear, to see where that's maximized. You look at the instability. You compare the forecast model runs and how they're initialized with what is actually happening to see if they're accurate right off the bat. And so once you basically narrow down a target area, that's when you get everybody organized, everybody piles into the Dominators, and then we hit the road. And once you're in the target area, then you start looking at satellite imagery, you start looking at radar, you use your eyes a lot to try to find where storms are developing. Your eyes are extremely important in the field because you could pick out which storms have very strong updrafts, which ones may not look as good visually, and many times your visual interpretation with the storms with your eyes will be very different than what your data is telling you, or the radar or satellite. It's basically a combination, a hybrid approach with storm chasing between using your eyes and analyzing all the data available to you using mobile internet. And then once you're really close to the tornado, then I've got my head out the window, looking straight up at it, trying to see just how wide the tornado is going to get. And we try to position ourselves just on the northwest side of the tornado. And this area is called the Bear's Cage. So I've always liked the Bear's Cage because you can easily assess how wide the tornado is going to get. You can monitor that clear slot that tightens up the rotation, and you can see just how wide it might get to.
There it is, look at the funnel. Look at the needle funnel in the middle. See it? All the way down, all the way down. Boom. Yes, right now we've got a massive tornado. This is a cone tornado turning into a wedge, very strong southwest of us. When a tornado is not moving side to side, it's coming right at you. This one is coming right at us.
And if there's not a well-defined clear slot, and it looks like the tornado might have a lot of potential to expand rapidly and intensify, that's when that we might want to hang back a little bit and then intercept once it matures and you're aware of how big that tornado is going to get. And in the Bear's Cage, a lot of times the lighting is also the best too. You'll have it'll be backlit and you can just see a well-defined tornado and you're just northwest of it. And if that tornado gets too intense, you can always stop. You can put on the brakes and let the tornado move by.
All right, it's a textbook rotating wall cloud right here. Just had cloud to ground lightning in the vault. That area between the wall cloud and the rain core is the vault. And that's a rotating wall cloud right there that could become a tornado at any time. You can see it's starting to get some rotation already. Got the updraft of the storm and then the downdraft over here where all the rain and the hail is falling. You can see the hail streaks.
And so that's why, even though, despite its name, I feel most comfortable in this area. I almost consider it the womb of the supercell. It's like you're in this little area of inflow where there's not much rain and all the circulation is going around you. That curtain of rain is wrapping all around you. You see this tornado. And you have the inflow air where it's meeting the cold air from the rain core, and everything comes together near the Bear's Cage, but it's just northwest of the tornado. So if it gets way too intense, I think it's a very safe spot for us when we're moving in to intercept a tornado and we're not sure how strong it's going to get. So once we're in our target area and we're watching storms develop, they start off as puffy white cumulus clouds, and then they'll continue to grow and they become cumulonimbus clouds, or thunderheads, and those are those massive nuclear explosion-like clouds. And if the ingredients are in place, if you have that wind shear, or if the instability is high enough, then those will start to rotate. And those cumulonimbus clouds are the updraft of the storm, but then as the storm matures and develops, rain and hail, sometimes up to the size of baseballs and softballs, gets too heavy for the updraft to support, and then it falls down. And then that's the formation of the downdraft of a thunderstorm, or in this case, a supercell. So you have the rotating updraft of the mesocyclone, and then you have the downdraft where all the rain and the hail falls. And if the wind shear is sufficiently strong, then that downdraft is kept separate from the updraft, and then you get a long-lived storm that's more likely to produce tornadoes. So once you get a supercell storm, what you'll see visually, and a lot of times you'll see the tornado genesis and you'll see precursors visually to tornadoes forming way sooner than your data or radar will show you. And that's why storm chasers are so important in the warning process, because what we could see underneath the storm by visually observing firsthand that ground truth, we can predict tornadoes forming a lot faster than you could with just analyzing radar. And it's that the National Weather Service forecasters and media use that whole suite of information. You've got the storm chasers in the field, you've got the radar, you've got all the computer models, the surface observations. Now as storm chasers, we have live streaming video to provide that ground truth to forecasters to help increase warning lead times. And all that information goes in to the watches and warnings that you see on TV that you need to heed and should be prepared for to keep your family and loved ones safe. So once we have a supercell, one feature that always seems to characterize the real prolific tornado producers is a massive updraft base. So you have a supercell with an updraft and a downdraft, and on the bottom part of that updraft where you basically see this explosive cloud matter lifting up, the bottom side is called the cloud base. And that's when you basically have parcels from the ground that are lifting up in the updraft and they cool, and then when they condense, they'll become cloud matter, and that's the updraft part of the storm, the pancake stack mesocyclone. But that big, crisp updraft base, if you have a very large base that stretches horizontally for a long distance and is very crisp, that shows that you have a very strong, thick updraft. And once that wind shear gets going, it's much easier for that to form into a tornadic mesocyclone. But you'll get this massive updraft base, and you can see the rain core to the right with the downdraft, and then you can see the updraft base with the updraft rotating, pancake stack, and then a little bit of air will feed underneath that updraft base from the rain core, and that creates condensation and a lowering of the base. And a lot of times you'll get this blocky wall cloud, as we call it, that'll form. And a wall cloud, by definition, is just a cloud element that hangs below the cloud base. If you have a lot of wind shear in that level, the inflow feeding into the storm, that can cause the wall cloud to start to rotate and tighten up, and you'll get dry air from the back of the storm wrap all the way around the wall cloud, tighten up the vortex, and then you have that intense updraft of the mesocyclone that finishes the job.
The most textbook representation of a wall cloud you can get. Right now we're in central Nebraska. This is a sculpted, beautiful supercell. If you pan up, you'll see the bigger mesocyclone, and that's just the rotating updraft of a supercell thunderstorm. That's what defines a supercell thunderstorm, is just a storm with a rotating updraft or mesocyclone above it. And look at that pancake stack. This is likely going to put down a tornado right underneath the wall cloud, or the right side of the wall cloud or north side of the wall cloud is where you're going to get that tornado.
But once a tornado's on the ground, they usually will go through different stages in their life cycle. When a tornado will first touch, a lot of times the circulation will be relatively broad. That dry air or clear slot from behind the storm will wrap in and cut into the mesocyclone and tighten the circulation. As that dry air wraps around it and the supercell moves on, eventually the dry air becomes so dominant that it starts to tighten up the vortex. And that's called the rope out phase. And when that dry air wraps all the way around and cuts it off from the main updraft or the inflow that the supercell is ingesting, that's when you get a rope out. And a lot of times the strongest wind speeds in tornadoes occur during this rope out phase, because as it's tightening and tightening, the angular velocity is increasing. That rotation is increasing dramatically. Just like that figure skater reference, when they're spinning in a circle and they pull in their arms, they spin faster. And that's also why a tornado's size isn't always representative of its strength. All tornadoes are different. But they do have these well-defined life cycles where they'll touch down and that dry air will cut it off from the main supercell updraft. It's called occlusion. It'll rope out. And then if the ingredients are still in place for tornadoes, the supercell can cycle and produce another one. And that's called a handoff.